Welcome to video number 17 for Physics 102. In this video, we introduce the subject of thermodynamics and begin to explore a molecular picture of matter. This video begins our final unit, the subject of thermodynamics. Up to this point in this course, we've been thinking about forces on matter as a whole. We've been asking questions like, if I apply a force to a crate, what's the resulting acceleration? And so forth. In every case, we're talking about a box, or a car, or a person. A macroscopic object, and we're exploring what happens to that object as a whole. In thermodynamics, we're going to begin to apply our ideas of energy to the very molecules that make up matter. And at the same time, we are going to connect phenomenon that happens at the world of molecules, which is picometers, 10 to the minus 12, to a phenomenon that we can observe on our distance scale, about 1 meter. These are the two goals of this unit. Let's begin by thinking about atoms and molecules. One of the most important things about molecules, from a physics perspective, is that they're always moving around. For example, in a solid, such as sodium chloride, pictured here, the atoms and molecules are arranged in a crystal lattice, as you may have discussed in a chemistry class. However, the molecules aren't just fixed to these sites. They're actually moving around and vibrating about the fixed lattice sites. They're always jiggling around. For a gas, in contrast, such as the gas in these balloons, the molecules are free to completely move around the container. They can go anywhere within the volume. However, in both the solid and the gas, the molecules are moving. Throughout our study of thermodynamics, we'll spend a lot of time discussing the ideal gas because it's one of the simplest systems we can study. In order to understand the ideal gas approximation, it's probably best to compare it to a real gas, such as the oxygen or nitrogen in the room around you. In a real gas, the gas is made up of particles with some small but not exactly zero volume. In the ideal gas approximation, we assume that the molecules have exactly zero size. Similarly, in a real gas, the molecules attract each other ever so slightly through van der Waals forces and the like. An ideal gas molecule, however, does not attract another ideal gas molecule. They don't interact with each other at all. Also in our analysis of the ideal gas, we will typically ignore gravity. We'll just turn it off and pretend it doesn't have an effect. These assumptions may seem to have no connection to reality. I mean, a gas of particles of zero size that don't interact with each other and have no impact by gravity, those seem like fairly unphysical conditions. However, if you think about an oxygen molecule, its volume is 10 to the negative 30 meters squared, which is very, very small compared to the room you're in. So the approximation that a gas has zero size for its particles is not actually that bad. Similarly, the force of the hydrogen bond is something on the neighborhood of 10 to the minus 10 newtons, which is again, very small force. So the idea that ideal gas molecules don't attract each other at all is not a terrible approximation. In fact, carbon dioxide gas behaves like an ideal gas to 0.5% accuracy at everyday pressures and temperatures. So we can use the ideal gas to get a very good idea of how real gases are behaving under a variety of typical conditions. Let's explore the consequences, however, of this ideal gas approximation. So, first, we've turned off gravity. What effect does that have? Well, without gravity, the particles have no gravitational potential energy. Only kinetic energies are possible. There's no G for the MGH. Furthermore, without gravity, particles travel in a straight line until they run into something. They do not follow the parabolic arcs that we've been studying in our third unit. Now let's explore the consequences of the fact that ideal gas particles have zero size and zero intermolecular force. Well, two particles of zero size cannot collide. Think about that one for a minute, but you'll see it's true. Since they can't collide with each other, the particles only hit the walls. The combination of these two approximations means that ideal gas particles travel in straight lines until they hit a wall. So now that we understand what an ideal gas particle is, let's begin to think about their kinetic energy. Well, we know that molecules are moving, but not all the molecules in a material are moving with the same speed. Here you can see the speeds of oxygen molecules as a function of temperature. The blue shows you the distribution of speeds for oxygen molecules at 26 degrees Celsius, and the red shows you the speed of oxygen molecules at 927 degrees Celsius. Now, this is physics, so instead of speed, let's think about kinetic energy, where the kinetic energy of a single molecule is still 1/2 mv squared, where m is the mass of the molecule, and v is its speed. Now we could characterize the gas in a couple of different ways. One, we could just add up the kinetic energy of all the molecules in the gas. Just add them all up. This seems like a daunting prospect for many gases because of the number of particles, but we'll see that this has an interesting idea later. Another idea we could think about is we see that these distributions have some average speed. The average here is VRMS. This is the average speed of the molecules. We could use this average speed to calculate an average kinetic energy, 1/2 mv squared, m being the mass of the molecule, and instead of the v of each individual molecule, we're using the average speed. This bar in this equation above the k means that we're considering the average kinetic energy. So let's think about these two different ways of approaching the kinetic energy of a gas. We could either add them all up or think about the average. Let's begin by considering adding them all up. This will lead us to a concept called internal energy, which we'll indicate with the letter U. Now, an ideal gas only has kinetic energy. There's no potential energy between the atoms. In a solid, however, there are chemical potential energy associated with the bonds between the different atoms. If we were to add up the kinetic energy of all the molecules in a material, as well as add up the chemical potential energy in all the bonds, we would get the total internal energy of the material, U. Note, we're only including the internal energies, the energies of the molecules themselves. We're not including the energy associated with the molecule in some sort of external force. This is perhaps best illustrated by an example. So let's say we have two solids, one on the ground and one up at the top of the Empire State Building. These two solids have different heights, but are otherwise identical. They have different gravitational potential energies due to their different heights, mgh. However, the internal potential energy of all the bonds is the same, and the internal kinetic energy is the same. If we were to add up the kinetic energy of all the molecules in these solids, we would get the same number. It would be non-zero because the molecules are jiggling around, but it would be the same non-zero number. So these two boxes have the same internal energy U. Even though they have different gravitational potential energies, they have the same internal energy U. So now we've thought about adding up energies. Now let's think about taking the average of energies. We can see in these distributions that the average speed, and therefore the average kinetic energy, has a dependence on temperature. At low temperatures, the average speed is 484 meters per second. At higher temperatures, the average speed is 967 meters per second. So we see a connection between average speed, therefore average kinetic energy, and temperature. This connection is the definition of the modern definition of temperature. Temperature is a measure of the average kinetic energy of the molecules. We'll get into the exact details of the equality later, but right now, what's important to understand is that if the temperature goes up, the average kinetic energy of the molecules has also gone up. Since temperature is defined as an average, you can't define the temperature of a single molecule. It's not a defined concept. This modern definition of temperature leads to a new idea, absolute zero. If temperature is related to the average kinetic energy of the molecules, and the kinetic energy of a molecule is related to its speed, well, speed has the smallest possible value, 0. The molecule is stopped. Therefore, temperature has a smallest possible value, absolute zero. At absolute zero, which is minus 273 degrees Celsius, all molecular motion stops according to classical physics. The molecules are just sitting there, not vibrating, not moving at all. According to classical physics, that's what goes on at negative 273 degrees Celsius. Classical physics is all that physics discovered before 1905, which is everything we've talked about in this class falls into that category. Now, in reality, some odd modern physics, quantum mechanics in particular, kicks in, but the idea of a lowest possible temperature still exists, and it's still negative 273 degrees Celsius. This idea of absolute zero allows us to construct a new temperature scale. You're probably familiar with the Fahrenheit and Celsius temperature scales. These are based upon boiling and freezing points of water, where the freezing point of water is 0 Celsius or 32 Fahrenheit, and the boiling point of water is 100 Celsius or 212 Fahrenheit. Notice that the difference between these 2 points is 100 Celsius or 180 degrees Fahrenheit. Therefore, Celsius degrees are bigger than Fahrenheit degrees. If you wanted to convert between a Celsius temperature Tc and a Fahrenheit temperature Tf, this is the expression you would use. However, the idea of absolute zero motivates a new temperature scale, Kelvin, the Kelvin temperature scale. Absolute zero is defined to be 0 Kelvin. Note we say 0 Kelvin, not 0 degrees Kelvin. Similarly, we don't put the little degree symbol when we write Kelvin temperatures. However, while the 0 points are different, 1 Kelvin is the same size as a degree Celsius. So the difference in temperature between the freezing point of water and the boiling point of water is 100 kelvins. For Celsius, it goes from 0 Celsius to 100 degrees Celsius, while from kelvins, it goes from 273 Kelvin to 373 Kelvin. So 1 Kelvin has the same size as 1 degree Celsius. The only difference is the starting point. So in order to convert from a Celsius temperature to a Kelvin temperature, we simply add 273.15. Now that we have a definition of temperature, we can connect all the different properties of an ideal gas. Let's assume that the helium in these balloons behaves like an ideal gas, which is not a bad assumption. This ideal gas is characterized by a couple of different properties. Its volume, how big is the balloon, its pressure, which you should be able to figure out the pressure in these balloons from our discussion of fluids, how much gas is in the balloon. We will express this in terms of the number of moles, which we'll indicate by the letter little m. I'm assuming you're familiar with the idea of moles. If you are not, please review section 14.1 in your book. If you are still confused, please come and see either a TA or a preceptor. And of course the gas inside a balloon also has a temperature. If we measure this temperature in Kelvin, and only if we measure this temperature in Kelvin, we can connect all of these different variables into an equation known as the ideal gas law, where we have the pressure times the volume is equal to the number of moles, R, times the temperature T, where R is a fundamental constant of the universe, 8.314 joules per mole Kelvin.